My name is Siqi with Sotiris. We're presenting our work, Control Barrier-Aided Teleoperation with Visual-Inertial SLAM for Safe MAV Navigation in Complex Environments. This is a joint work with our supervisors, Professor Stefan Leutenegger and Professor Schoellig. Micro-area vehicles, or MAVs, are required to safely operate in increasingly complex and unstructured environments that are not necessarily known a priori. In this work, they propose a perception-based safety filter that leverages control barrier functions in conjunction with Visual-Inertial SLAM and dense 3D occupancy mapping for guaranteeing the safe operation of teleoperated MAVs. Our work relies on three bodies of the literature, specifically Visual-Inertial SLAM, which provides consistent state estimates and map based on camera images and AMU measurements. Volumetric mapping that focuses on creating a dense 3D map of the environment. And lastly, safe control that guarantees safe operation with respect to given constraints in the presence of uncertainties. In this work, we combine the three ingredients and formulate a perceptive CBF safety filter based on an online dense volumetric map constructed using only onboard sensors. We show in real-time experiments that the overall system guarantees the safe operation of teleoperated MAVs without the need for any external infrastructure.
Here is an overview of our proposed approach. In our setup, the MAV system is equipped with an IMU, a stereo camera, and a depth sensor. We use OCVIS2 for onboard state estimation, a state-of-the-art optimization-based visual-inertial SLAM system. Based on the state estimates and depth images, a 3D volumetric map of the environment is created online for safe navigation. The plot on the left shows an occupancy field slice after the integration of a single depth image, and the plot on the right shows the corresponding truncated Euclidean sign distance function slice. The control barrier function for the safety filter is defined by the TSDF, which has positive values in safe space, negative values in unsafe space, and is 0 at their boundary.
Based on the feedback from the perception module, the safety filter is then designed to modify the operator references as required to avoid constraint violations. Our safety filter is designed based on a control barrier function, which is derived from a dense volumetric map constructed in real time using onboard sensors. Now we take a closer look at the safety filter formulation, which aims to find a certified input U that best matches the teleoperator input while satisfying the CBF condition. Here, H is the control barrier function that is obtained from the TSDF. It has positive values for safe regions and negative values for unsafe regions. It is 0 at the boundary. F here is the dynamic model of the MAV system. And alpha is a constant slope that is negative inside of the safe set and positive outside of the safe set. If the system starts inside of the safe set, the CBF condition has two implications. At the boundary, the change in the CBF value is lower bounded by 0. This means that the system can either move along the safe boundary or move towards the safe region. Inside of the safe region, the change in the CBF is lower bounded by a negative value. The system is allowed to move towards the safety boundary, but at a rate limited by the slope alpha. This overall condition ensures that if the system starts inside of the safe set, it will remain inside of the safe set. To simplify the optimization problem, we use a first-order approximation of the CBF constraint, which allows us to formulate the safety filter as a quadratic program that can be solved efficiently online. We can also introduce an additional term here to account for the noise in the system. Here, epsilon is an upper bound on the magnitude of the system noise. After computing the certified input, the input signal is then sent to a baseline controller of the MAV.
We verify our proposed approach in real-time teleoperated quadcopter experiments. In the experiments, the Visual-Inertial SLAM produces state estimates at 60 Hz, the occupancy map is updated at 10 Hz, and the safety filter is applied at 6 Hz. We tested our approach in 4 distinct environment configurations. In each configuration, the operator instructed the vehicle to navigate from one point to another. Equipped with the perceptive safety filter, the MAV autonomously avoids obstacles and unsafe regions by making minimal adjustments to the operator's references. Here we see the safety filter guides the MAV to fly higher to achieve a larger clearance from the obstacles below. The safety filter also enables the MAV to navigate through relatively tight spaces without collisions. We proposed a perceptive safety filter that integrates CBF certification with Visual-Inertial SLAM and dense 3D occupancy mapping for safe teleoperated navigation of MAVs. The environment map and the CBF are updated in real time, solely relying on the onboard sensors and computation resources. The proposed perceptive safety filter was verified in real-time experiments.
This concludes our presentation. Thank you for watching.